Oh, welcome and thank you for joining again. We'll continue with another question from the textbook on page 83, number 26. So, let the point P with coordinates A and B be a point on the curve square root x plus square root y equals 1. We have to show that the slope of the tangent at the point P is negative the square root of b over a. So in other words, what we're asked to find in here is the slope of the tangent drawn at a and b. So we know that slope of a tangent means derivative. So that means we have to find dy dx. So as you can see in here, we have the square root of x, the square root of y equals 1. Now, in order to differentiate square roots, we use the square roots in power form. So we'll rewrite the equation slightly differently. I'm going to make this a little lighter. All right, so we have x to the power of 1 over 2 plus y to the power of 1 over 2 equals 1. So in order to differentiate this function, what we're going to do is differentiate each side of it. You see that both x and y are like regular terms in here, but y is the dependent variable and x is the independent variable. And we're differentiating in terms of x. So we're going to say we're taking the ddx of x to the 1 over 2. We're taking the ddx of y to the power 1 over 2. And obviously, we're going to take the ddx of number 1. So remember that when the variables in the expression or in the function or in the term match the variable in the derivative, which means that you are differentiating a function that is dependent of x, directly dependent on how x is changing, the speed of change of x on dx. We call this explicit differentiation, which means in simpler words, we're just differentiating it by using whatever formula or whatever rule we have in hand. So we're going to have the derivative of x to the power 1 over 2 equal to, based on the power rule, 1/2 of x to the power of 1 over 2 minus 1. And then plus. Now, when you look at the second term, you see that we have to differentiate y in terms of x. So the variables here don't connect. So if you ask to find how fast y is changing when x is changing at a certain point, and you don't know any connection between y and x, then we're going to think, oh, there must be some hidden connection between y and x. So y must be represented by some function dependent on x. So there is something hiding here. So we are going to say that this is what we call implicit differentiation. And we call this implicit differentiation because we are implying that the value of y is dependent on x. And that's why we are trying to measure how fast y is changing when x is changing. So, and just to actually clarify, this was explicit because we had a direct relationship between the variable in the expression differentiated and the variable in terms of what we are differentiating here. So what or how do we deal with a term like this? So first of all, you can look at it as some chain. So you can look at function y as the outside function that has an inside function dependent on x, which we are unaware of. We don't know what exactly the equation is. So we are differentiating the outside function, and we're going to say that the derivative of y to the power 1 over 2 will be 1 over 2 and then y to the power 1 over 2 minus 1. But because we know that y must depend on x somehow, so there is an inside function hiding in y, then we'll have to also multiply by dy dx. So remember that the function y is an outside function which we are implying that is dependent on x. And on the other side, we have the derivative of 1, and this is the easiest term to differentiate. The derivative of a constant is 0 because the change of a constant is 0, and change and derivative means the same thing. So let's check and see what this expression becomes. 1 over 2 x to the power 1 over 2 minus 1 will be x to the power 1 over 2 x to the power negative half. And then we have 1 over 2 y to the power of 1 over 2 minus 1, so that's negative half. And then multiply this by dy dx. Remember that our goal here is to find dy dx, so we are trying to isolate dy dx, which means that dy dx, which is going together with this term, so it has a factor 1 over 2y to negative 1 over 2, can stay on the left side on its own. So we have 1 over 2 y to the power negative 1 over 2 dy dx is equal to, we're going to take 1 over 2x to negative half to the other side. So we have 1 over 2x to the negative half, and because we're taking it to the other side with a minus in here. So we're trying to, again, isolate this, which means that what we can do is divide both sides by 1 over 2 y to the power of negative half. So I'm going to leave this as is for now. Obviously, you can simplify it in different ways as well. So 1 over 2 y to the negative 1 over 2. And as you can see, again, we can simplify the 1 over 2. We can simplify the entire thing here. And dy dx is getting close to being isolated. So we'll have x to the power of negative half over y to the power of negative half, and we have a minus in front of it. Now, as you can see in here, we have powers that are negative, so we want to make them into positive powers, because positive powers are easier to evaluate. The minus will stay where it was. The fraction will stay where it was. But now y to negative 1 over 2 will jump to the numerator so that its power becomes positive. And x to the negative 1 over 2 will go down to the denominator, so its power is positive as well. So in other words, what we obtain in here is, let's add another page, negative, and you see, since the powers are the same, we can bring them inside the same power, y over x to the power of 1 over 2. Or we can also say this is negative. Instead of power of 1 over 2, we can write the square root of y over x. Now remember that x and y are the coordinates of the point P with coordinates a and b, and we will substitute a and b into the derivative. So we have dy dx measured at the point P with coordinates a and b would equal negative square root, the value of y is b, and the value of a is, the value of x is a. And voila, we got the derivative at a point P equal to negative root of b over a. I hope this made sense, and thank you for learning with me. Bye for now.